polynomials, they have a finite last term. Namely, we've been ending with the nth term. So when we talk about a Taylor-Maclaurin polynomial, you have a definite end. In this set, and like I said, what we're going to now do is extend this notation for Maclaurin and Taylor polynomials by going to infinity. Since our upper index is infinity, we're going to call these Maclaurin and Taylor series instead of polynomials. So polynomials, remember, have the definite end. Series are going to go to infinity. So again, when you're taking a look at what we did the other day, again, when I had you write your Maclaurin polynomials in sigma notation, we were ending with the nth term, so that upper index with an n. So now that if we talk about the series, again, remember, a series has no end. The upper index for your sigma notation is going to be infinity. So when you generate the series, when you write it out, you'll start with the first couple terms. You'll have your plus dot 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 plus, ending with that generalization, plus, and make sure you always put the dot dot dots at the end to show that the series is going on to infinity. All right, so that's the biggest difference in what we're going to be doing today versus what we did on Tuesday. Again, we want to show that it is a series. So the Maclaurin series, remember, just like the Maclaurin polynomial, is where your center is at 0. All right? So again, whether it's a Taylor, because up here this is your Taylor series, or whether it's your Maclaurin, and Maclaurin is your Taylor series, again, the Maclaurin series just has that center at 0. You still want to make sure that upper index is infinity, and you have your plus dot 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 at the end when we're talking about the series. So again, remember a Taylor or Maclaurin series. Remember, Maclaurin series is a Taylor series. Like I said, the only thing that's changed is the upper index is infinity instead of n. So again, the n is when you're having to write the Taylor or Maclaurin polynomials. Okay? When you do have the nth Maclaurin and Taylor polynomials, for example, instead of having the series, if I was to stop with the second degree, this is what we call a partial sum of your Maclaurin or Taylor series. So when you're looking at a Maclaurin or Taylor polynomial, you're looking at the nth partial sum of this corresponding Maclaurin and Taylor series. So when you do write up a Maclaurin or Taylor polynomial, wherever you do end it, that is the partial sum for the Maclaurin and Taylor series. As I mentioned the other day, it is helpful to memorize and know some of the most common Maclaurin series. I guess you call it a good bad news situation if you ever do forget it. You can always generate it by hand, but as you can see, it can be very time consuming. And some of the problems, they're written to make you, to force you to know it, because you're not going to want to waste your time generating some of these by hand and then perform other operations that may be indicated in the problem. So some very common, and we're going to add these to your file folder, the Maclaurin series that you really should have memorized are these four. The e to the x, sine x, cosine x, and 1 over 1 minus x. They come up so much, and we do a lot of different variations on these different types of series that it is very helpful to you. So e to the x. So again, when I want to write this in sigma notation, remember to generate that general term, you always still want to write out the first couple terms of the series so you can see the pattern that's generated. E to the x, and you can refer back to page 2 of your notes if you forget what it is. It's 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus your dot 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 plus your x to the nth over n factorial plus dot dot dot. So if you're writing your series, this is how you have to write it. You write the first couple terms plus dot 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 plus what the general formula is plus dot dot dot. So that's how you write the series for a Taylor or in this case a Maclaurin. So then in sigma notation, we're starting with n is equal to 0. Remember that upper index is infinity, so it's going to be your x to the n over n factorial. So that is your Maclaurin series for e to the x. like I said, the n or the k, the variables are interchangeably. It doesn't matter whether you're writing it as a k or writing it as an n. Okay? Sine of x. Remind me again from trig, sine is what kind of function, odd or even? Odd. So remember what powers are going to remain when you generate your sine of x series? The odds. So remember with sine of x, do you start with 1 or do you start with x? Well, sine of 0 is 0. So we start with x. So x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus your dot, dot, dot plus. Remember, you need that alternator, so it's going to be your negative 1 to the k. You have x to the 2k plus 1 all over your quantity 2k plus 1 factorial plus your dot, dot, dot. So in sigma notation, you have k is equal to 0 to infinity. Your negative 1 to the k, x to the 2k plus 1 all over 2k plus 1 factorial. So there's your Maclaurin series for sine of x. Cosine of x from trig is what kind of function? We know that's your even. So again, only the even powers are going to remain for the Maclaurin series for your cosine of x. Remember, this is going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus your dot, dot, dot plus. You have the negative 1 to the k, x to the 2k, all over the quantity 2k factorial, plus your dot, dot, dot at the end. And in your sigma notation, the Maclaurin series for cosine of x starts with k is equal to 0 to infinity. You have your negative 1 to the k, x to the 2k, all over 2k factorial. So any questions on, again, and I had you generate these by hand in your notes in the last section. 1 over 1 minus x is a very common Maclaurin series. This is actually your Maclaurin series for a geometric series. Because if you think about how you find the sum of an infinite geometric series, you always take your first term and you divide it by 1 minus r. So this is actually your geometric Maclaurin series, the 1 over 1 minus x. So again, this particular series is 1 plus x squared plus x to the third plus x to the fourth plus dot, dot, dot plus. What do you think the general formula would be for this particular series? X to the what? X to the k. So then in your sigma notation, this is just going to be k is equal to 0 to infinity of x to the k. So like I said, these are your 4 common ones that come up quite a bit. And eventually we do so much with those 4, you're probably going to have them memorized anyway, because we do so much with them. And you're not going to want to keep on generating these things by hand over and over again. All right? So let's take a look now at a power series. So if you have a variable in the infinite series form that we've been writing from k is equal to 0 to infinity, we call this a power series. And when you have a power series centered at 0, we have what actually is called a Maclaurin series. It's a Maclaurin power series. So every Maclaurin series is a power series. Taylor is also considered a power series, and we'll talk more about the Taylor power series later. So every Maclaurin and Taylor series is a power series. Again, the power series is just the sum where you've got your variable x raised to a power. That's why it's called a power series. All right? So x to the k is just simply 1 plus x to the squared plus x to the third plus your dot, dot, dot plus your x to the k plus your dot, dot, dot. And remember, this is actually your geometric series of 1 over 1 minus x. X to the k over k factorial is actually 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus your dot 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 plus your x to the k over k factorial plus dot dot dot. And this one's equal to what? Remind me again? E to the x. So we also call this the Maclaurin power series. Okay? This one, just by looking at it, hopefully remember which Maclaurin series is this one going to be? Cosine. So it's going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial plus your negative 1 to the k, x to the 2k, all over 2k factorial. And again, this is your cosine of x. So like I said, a power series is just this infinite series that has your variable x raised to some power. It's an exponent, a real number. All right? Now, the nice thing about knowing those 4 common series is if you know e to the x, sine x, cosine x, and 1 over 1 minus x, and you recognize that Maclaurin series, then you're going to be able to generate variations of those types of series without having to generate them by hand. In other words, it's almost a shortcut to generating other Maclaurin series. Again, instead of having to write out your f of x, f prime of x, f double prime of x, etc., this is some variations on your common Maclaurin series. Again, this shortcut, we can basically come up with other Maclaurin series by substitutions. Again, this substitution method only works if you're dealing with a Maclaurin series. If it's a Taylor, you've got to unfortunately still do it the long way. So for example, take a look at 1 divided by 1 plus x. Do you agree with me another way I could write 1 over 1 plus x is 1 over 1 minus negative x? Do you agree with that? They're equivalent expressions. So I know, or hopefully eventually you will have memorized, the Maclaurin series for 1 over 1 minus x, which is 1 plus x squared plus x to the third plus dot 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 plus x to the k plus your dot dot dot. So by substitution, because if you know 1 over 1 minus x, the only thing I'm going to have to do to generate the Maclaurin series for 1 minus negative x is simply just substitute. Take out the x and replace it with a negative x. So 1 plus negative x to the second plus negative x to the third plus dot 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 plus your negative x to the k. So it's going to save you a lot of time because now you're going to be able to do variations of other Maclaurin series. And if this was maybe like a 1 minus 2x, then all you'd have to do is replace x with a 2x. So it's going to save you a lot of time than having to generate these Maclaurin series over and over again. All right? So then I know that this is 1 minus x plus x squared minus x to the third plus. Now, a lot of times we're used to seeing the alternator as a base of negative 1. So instead of seeing negative x raised to the k power, for a lot of these variations, what you're going to see is that negative 1 to the k, x to the k. They're equivalent. It's not incorrect if you left it as negative x to the k, but a lot of times they do break out that alternator. So then we want to use sigma notation to write the series. So that in sigma notation, this is going to be equal to k is equal to 0 to infinity. Again, make sure that upper index is infinity, x to the k, with your alternator negative 1 to the k. Okay? So that's how you can use a Maclaurin. Has the series 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus your dot 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 plus negative 1 to the k, x to the 2k, all over 2k factorial. So if you know what the Maclaurin series for cosine of x is, then you can find the Maclaurin series for cosine of pi x. because all you're going to do is take out your x's and replace it with a pi x. So 1 minus pi x to the second power over 2 factorial plus pi x raised to the fourth power over 4 factorial minus pi x to the sixth power over 6 factorial. So then when it comes to generating your general term, we can just simply replace your x with a pi x. Again, this substitution only works if you're dealing with a Maclaurin series. If it's a Taylor, you've got to go back to the long way and generate it the long way. So then in my sigma notation, I'm going to have k is equal to 0 to infinity, negative 1 to the k, pi x raised to the 2k, all over 2k factorial. So any questions on how you can use some of your common Maclaurin series and do the substitution to come up with other series? So you don't have, again, this is the shortcut, so you don't have to generate them by hand. All right? So when you're dealing with a Taylor, again, remember when you're dealing with a Taylor series, remember this is when you're dealing with your sigma n is equal to 0 and to infinity. It has no end. Again, unfortunately, ladies and gentlemen, even though, for example, number 3, it's an e to the negative x, the center is not at 0, so you are going to have to generate these Taylor series the long way. You're going to just have to do it by hand. That substitution method does not work because the center is not at 0. So in order to write your sigma notation, you're going to have to write out the first couple terms so that you can see what the pattern's going to be in order to come up with that general formula. So again, remember the way you're going to generate a Taylor is we first have to find f of natural log of 2 plus f prime of natural log of 2 times x minus natural log of 2 plus your f double prime of natural log of 2 times x minus natural log of 2 to the second power over 2 factorial. And again, you probably need to at least take it out to the third degree or third order to really establish what the pattern's going to be. Because you've got to see the pattern in order to come up with that general term. So just like you had to do last night for homework when you had to generate the Maclaurin and Taylor polynomials, first of all, you know that f of x is equal to e to the negative x. So f of the natural log of 2. So what is e raised to the negative natural log of 2? And no, it's not negative 2. Remember, before you can apply that composition rule of e raised to the ln, the coefficient of ln has to be a positive 1 in order to apply that composition rule. So you have to rewrite negative natural log of 2 as natural log of 2 to the negative first. So what is f of ln of 2 going to be equivalent to? 1/2. So remember that composition rule of e raised to the natural log, that coefficient of natural log has to be a positive 1. So now, let's talk about f prime of x. What rule are we going to have to use to take the derivative of e to the negative x? We have to apply your what? Chain rule. So that's going to be negative e to the negative x. So then f prime of natural log of 2 is going to be what? Negative 1/2. The second derivative of x, what's the derivative of negative e to the negative x? That's just going to be what? E to the negative x. So then f double prime, or to the second derivative of natural log of 2, then is going to be equal to 1/2. And then you can see that the pattern that's developing, the third derivative of natural log of 2 is going to be negative 1/2. So then to plug these values into my Taylor series that I've started, f of natural log of 2 is 1/2 plus f prime of natural log of 2 I found was negative 1/2, so that's going to be a negative 1/2 times x minus natural log of 2. Second derivative is going to be 1/2 times x minus the natural log of 2 squared. And again, that 1/2 is being multiplied by the x minus natural log of 2 squared over 2 factorial. And then minus 1/3 times x minus natural log of 2 to the third all over 3 factorial. Oh, whatever a third, you're right, half, thank you. And again, I could go on and on. So now let's talk about what this general formula is going to be. First of all, am I going to have to include an alternator? Yes, so it's going to have to be a -1 raised to the nth. Again, you want to make sure I'm starting with the 0 term, so I want to make sure that that first term is positive. So make sure that your exponent for your alternator will truly generate the sign that you need for the first term. So then let's take a look at what else you're going to need in the numerator. What else are we going to need in the numerator of this general form? We're going to need that x minus natural log of 2 all raised to the nth power. Because here's your 0 term, first term, second term, third term. Over. So we have a 2, 2, 2, 2. So I'm going to also have to include a 2. What else is going to be in the denominator? 2 times what? N factorial. Do I need to have parentheses? No, you don't want to have those parentheses around the 2n factorial. Okay? So any questions or where I came up with a general form? So that in sigma notation, I can translate this into n is equal to 0 to infinity, -1 to the nth, x minus natural log of 2 to the n, all over 2n factorial. So there is your e to the negative x Taylor series centered around natural log of 2. Okay? You guys go ahead and try number 4 for me. When you're doing problems like this, ladies and gentlemen, if you end up with a number raised to an exponent, don't evaluate, don't multiply it out. Because in order to recognize what that general term is going to be, you need to be able to see what's happening with those powers before you multiply them out. So don't multiply. So for example, if you end up with like a 2 to the second, 2 to the third, 2 to the fourth, leave it like that when you're expanding out your Taylor series so that you can see the pattern that's needed to generate that general term. So you guys go ahead and try numerator. Coefficients that developed. I know that 2 is equivalent to 2 factorial. 6 is equivalent to 3 factorial. And if I look ahead, if I did actually find the value of the fourth derivative at x equals 3, notice I know that this would give me a 24 over 5 to the 5th. So I do know that this would have been equivalent to 4 factorial. So what's going to end up happening with the factorials in the general term? The general term, the factorials are going to end up doing what? Canceling out, exactly. So when I write my general term, first of all, am I going to need an alternator? Yes. So I have a -1. Again, I want that first term to be positive, and I'm starting with n is equal to 0, so it's going to be a -1 to the 0. Remember, the factorials are going to end up canceling out. So I'm left with an x minus 3 raised to the nth power. I'm sorry? Oh yeah, I'm right at 0. I'm sorry, -1 to the n. Thank you. Now, let's take a look, ladies and gentlemen, at what the denominator is going to look like. Remember, I'm starting with the 0th term. So I have a 5 to the first in my 0th term. I have a 5 to the second when n is equal to 1. I have a 5 to the third when n is equal to 2. So what is that exponent going to be then for 5? It's not going to be n, but it's going to be a what? N plus 1. So then to place this in sigma notation, it's going to be n is equal to 0 to infinity, -1 to the nth, x minus 3 to the nth, all over 5 raised to the n plus 1. That's why what I was mentioning at the beginning, you don't want to evaluate those powers. Leave it in exponential form. That way when it comes to writing the general term, you can identify what the pattern is going to be. You guys go ahead and try number 5 for me. So you agree with me let's just ignore the 1 for right now. Taking the 1 out of consideration, do you agree with me that there is definitely a pattern that's being established with that n equals 1 term? There's definitely a pattern. So just like when we talked at the very beginning of Chapter 9, we concern ourselves with the behavior as we're going to infinity, not necessarily what's happening in the beginning. So when you see a series, and this sometimes happens, the pattern may not develop until n equals 2, n equals 3, n equals 4. So in some series, that pattern doesn't actually develop. So what happens is when you go to express your sigma notation, we're simply going to take this 1, because remember what sigma means. Sigma means a sum. So what I'm going to do with this 1 is I'm just going to add it to my sigma notation. So instead of that lower index starting with a 0 term, I'm going to start with where n is going to be equal to 1, because the pattern is starting when n is equal to 1. So let's talk now about what this pattern is going to look like. So I'm going to take the 1 plus. Again, my sigma notation, the pattern starting with n is equal to 1 to infinity. So if the pattern didn't start until the second or third term, you would just change that lower index to n is equal to 2, but n is equal to 3. But you would include those terms that you would have to add on to complete this Taylor series. Now, do I need to include an alternator? Yes. Now remember, we're starting with n is equal to 1. So at n is equal to 1, that first term is positive. So what is the power going to have to be for the alternator to assure that this term is going to be positive? N plus 1. Times x minus e to the nth. Now, let's take a look at these coefficients. We end up with a 1, a 2, a 6. We know 2 is equivalent to 2 factorial. 6 is equivalent to 3 factorial. If I took it out again, I'd end up with a 4 factorial. But I can't cancel a 2 factorial with a 3 factorial. However, what you can do is simplify your factorials, because really what you have here is you have an n minus 1 factorial divided by n factorial. So when you simplify your factorials, what you can do is you can rewrite n factorial as n times n minus 1 factorial. So what is going to be left in the denominator now of this general term? It's going to be what? N times what? E to the n. Okay? Yes, Nathan? You need to simplify it. When you're coming to the general term, you want to make sure you express that in simplest form. Okay, that was a good question.